An overhanging beam PQR is subjected to uniformly distributed load 20 kN per meter. So instead of a simply supported, this time we have given the overhang beam and we are interested to know the maximum bending stress. Whenever we have rectangular section, then we can locate the neutral axis and we can find out the value of the top fiber and bottom fiber where we have maximum stress. So this time we have top fiber at distance equal to C, as well as the bottom fiber is equidistance, that equal to C. We have width is equal to 24 and we have depth D is equal to 100 mm. So in this case the value of C will be same as the depth divided by 2, that is 100 by 2 is equal to 50 mm. Only we want here where is the maximum value of bending moment. To find out the reaction here, we'll convert the UDL into equivalent point load. We have W is equal to 20 kN per meter and the total length here will be equal to 2 plus 1 is equal to 3 meter. So we can convert this UDL into equivalent point load, that will be W multiplied by L at distance equal to L by 2. L by 2 is 1.5. So 1.5 will come somewhere here. So here I will show the value of equivalent point load, that equal to W into L is same as 20 multiplied by 3 equal to 60 kilonewton, and this load will act 1.5 meter. L by 2 is 1.5 meters. So this distance is 1.5 meter. Remaining distance here will be equal to 2 minus 1.5 is 0.5 meter. Let's say this point equal to point S where we have equivalent point load is acting. So use this figure only when to find out the reaction at point P and point Q. To find out the reaction here, we'll take the moment either of any support. So we have sum of moment of all forces. This time I will take the moment about the point Q. Clockwise moment will treat as a positive value and the total sum must equal to 0. So you have to focus on point Q. Py will make a clockwise moment and that will be the positive value, and the distance between P and Q is equal to 2 meter. So we have clockwise moment is positive, force is equal to Py and the distance equal to 2 meter. W into L is 60 kilonewton. Act distance equal to 0.5 meter from Q will be anti-clockwise. Anti-clockwise is negative, force is 60 and the distance equal to 0.5. It must equal to 0. So we have 30 divided by 2. In this case we get the value of Py is equal to 30 divided by 2 is same as equal to 15 kilonewton. And then we can apply the summation of Fy, vertically upward is positive, must equal to 0. Both the reaction we have assumed vertically upward, so we have Py plus we have Qy and downward load equal to minus 60, that must equal to 0. So put the value of Py is equal to 15. In this case we will get Qy is equal to 60 minus 15, that equal to 45 kilonewton. So we'll show the value of Py here, which one is 15 kilonewton, and the value of Qy is equal to 45 kilonewton. And then we'll construct the SFD and we'll observe that how many points here where the shear force diagram will cross the zero shear force line. So both the reactions are known here. Now we can develop here the shear force diagram. So shear force diagram will construct from point P. At point P we have reaction is 15 kilonewton. So we'll move vertically upward by 15 kilonewton. So this one is same as 15 kilonewton. Now from this point up to point Q we have UDL is acting, and even for Q2R UDL is acting, but one load is acting at Qy. So first of all we'll calculate the total downward force, that equal to 20 multiplied by 2 will be 40. So that is downward is minus 40. So 15 minus 40, that will be equal to minus 25. So at point Q we have shear force is 15 minus 20 multiplied by 2, that equal to 40 is equal to minus 25 kilonewton. So somewhere at this point here, let this point equal to point A where we have shear force is 0. Now the shear force is 0 at this point, that can be calculated here. This value is equal to W and this distance equal to, let's say, equal to X. For this region we'll calculate distance equal to X. Here the upward force is equal to 15, downward is equal to 20 multiplied by x. So to locate the point A, we know that the shear force at point A is equal to 0 is same as equal to positive 15 minus W is equal to 20 multiplied by distance x. So in this case we will get 20x is equal to 15, or we have x is equal to 15 by 20, that is 3 by 4. 3 by 4 is same as equal to 0.75 meter. So here x is equal to 0.75 meter, and the total distance from P to Q is equal to 2 meter. It means that we have remaining distance from point A to point Q will be equal to 1.25 meter. So at point A, one chance is that we have a maximum value of a bending moment because there is a sign change. Now at point Q here we have a reaction is 45, so from minus 25 plus 45, so you have to move vertically upward and you will attain a value equal to 45 minus 25 equal to plus 20. So this value will be equal to 20 kilonewton. 20 kilonewton and minus 20 kilonewton, so you have to join by straight line. Now in the given SFD diagram, the shear force changes the sign at point A and at point Q. So there is a chance here is that we have maximum bending moment at point A or the maximum bending moment at point Q. For point A we'll use this triangle area, and for point Q we'll use this triangle area. For this triangle we have height is equal to 20 and the base is equal to 1 meter. And for this triangle height is equal to 15 and the base is equal to 0.75. Naturally this area will be less because it is 15 into 0.75 divided by 2. So this will give the maximum bending moment, that equal to 20 multiplied by 1 divided by 2. So bending moment at point A will be the area under SFD, and we'll take this SFD area from P to A. This area is a triangle, so we have 1 by 2, we have height is equal to 15 and we have base is equal to 0.75. Is 5.625, that is kilonewton meter. Secondly, we can calculate the maximum bending moment at point Q also by considering this triangle. So we have bending moment at point Q is again equal to area under SFD diagram from Q to R, that is again a triangle, so that equal to 1 by 2. We have height is equal to 20 and we have base is equal to 1. So this value MQ is same as equal to the maximum value of a bending moment is equal to 20 kilonewton meter. So this value you have to use for calculation purpose. So by flexure formula we have maximum value of a bending stress is same as equal to the maximum value of a bending moment multiplied by the top fiber or bottom fiber. In this case both distance are same, divided by I. So we have maximum bending moment equal to 20 is the kilonewton meter, so we will multiply by 10 to the power 6. C is equal to 50 divided by BD cube by 12. We have base is equal to 24, depth is equal to 100, so we have cube of it, and divided by 12, that 12 will shift in numerator. So maximum bending stress in this case is close to 250, that will be megapascal. A simply supported beam of length equal to 3 times of L is subjected to the loading as shown in the figure. One load is acting at distance equal to L from the left support in upward direction, and one load is acting P downward from the right support at distance equal to L. It is given that the value of P is equal to 1 Newton, length is equal to 1 meter, and the M is equal to 200 gigapascal. The cross section is a square with a 10 mm by 10 mm. The bending stress in Pascal at the point A located at the top surface of the beams at a distance equal to 1.5 L from the left end you have to calculate. Now since we are interested here the bending stress at point A, so first we have to find out what is the bending moment at point A. Bending moment at point A we can find out by finding the reaction at the two support and we'll cut the beam at point A, and then we'll find out a bending moment. And then we'll think of how to calculate the bending stress on the top surface. If the bending moment exists at point A, then the value you have to calculate, and if the bending moment will be 0, the bending stress will also be equal to 0. So let's say we have support at B and C, and the two reaction is By Cy. We assume this reaction vertically upward. We are only interested in the reaction at B because we cut it at point A. So only By will find out, and therefore we'll take the moment about the point C. So we have sum of moment of all forces above C, and clockwise moment will assume is a positive value. This sum must equal to 0. The moment of By above C will be clockwise. Clockwise is positive. We have force is equal to By, and we have distance equal to 3 times of L. Moment of this force about point C will be clockwise. Clockwise is taken as positive. We have force is equal to P, and the total distance of this force from C is equal to 2L. Moment of this force above C will be anti-clockwise. Anti-clockwise will be negative. Force is P, and the distance equal to L is must equal to 0. So here L term will be get cancelled. Is common to all. So here 3 times of the reaction at point B is equal to By is equal to, we have positive value of P here, but 2 times, and this one is negative value of P. So if we shift it, we will get minus P. So we are getting here the value of By as a negative value, and is minus P by 3. It means that assumption is wrong. That is, a vertical direction shown is wrong. It means that the value of By at point P must be downward, and the magnitude is P by 3, and this one is a correct direction. Now we'll cut at point A here, and we'll show one more FBD to find out the bending moment at point A. So at point B here, we have By is to be shown downward, so this value is same as equal to P by 3. This force acting is equal to P. The distance between these two points is, that is P by 3, and P is equal to L. So this distance is L. And he says that you have to find out a bending stress at point A located at the top surface of the beam at distance equal to 1.5 L from the left end. From the left end means B. So this point here A at a distance equal to 1.5 L. So to find out the bending moment at point A, we will show here first shear force which was acting downward, and we'll use here anti-clockwise moment at point A. So we'll just find out here MA. So this time we'll take the sum of moment of all forces about point A. We have assumed anti-clockwise positive, so we'll take the anti-clockwise is positive, and the sum must equal to 0. P by 3 about point A will make an anti-clockwise moment, that is a positive value, and the distance is 1.5 L. So we have P divided by 3. This one is anti-clockwise is positive, and distance equal to 1.5 times of L. Moment of this force P about point A will be clockwise, and this clockwise you have to take as a negative value, and the force is equal to P, and this small distance will be same as equal to 0.5 times of L. Plus we have to show here the bending moment at point A. So that is anti-clockwise shown, so you have to take it positive value. Here 1.5 divided by 3 is 0.5 L. So it is 0.5 times PL, and this one is also 0.5 times of PL. So bending moment at point A will be equal to 0. If the bending moment is 0, then the bending stress at point A, which is MA multiplied by C divided by I. Since the value of MA will be 0, so we have bending stress also equal to 0. A simply supported beam of length equal to 6 meter carries a uniformly distributed load of W is equal to 2 kN per meter throughout its length. The beam section is a rectangular section with a width is equal to 60 mm and the depth is equal to 120. Bending stress at a point 20 mm below the top surface at a section 2 meter from the left support we have to calculate. So it's very much particular about the location of a bending stress from the top surface. You have to locate the value equal to 20 mm, and we have a distance from the left support where we have to calculate the bending moment. That distance equal to 2 meter. So we are interested on this fiber which is below the top surface and distance equal to 20 mm. We can mark here the location of the neutral axis. Neutral axis is at a distance equal to 60 mm, that is d by 2. So this one is a centroid, that equal to G. Horizontal axis is Z axis. Vertical axis will represent equal to Y axis. Total distance here from the neutral axis to the top fiber is 60, and the given location at a distance equal to Y from the neutral axis is 60 minus 20, that equal to 40 mm. So at this point we have to calculate the bending stress. Secondly, we are interested in the bending stress from the 2 meter from the left support. So for this purpose we have to find out the reaction here. We have given here the value of UDL, that equal to W, and we have UDL is same as equal to 2 kN per meter. And this is a case of simply supported beam, so we have the total downward force is equally divided between the two reaction at A and B. So reaction at A will be total load is WL divided by 2. So we have WL by 2, as well as BY is also equal to WL by 2. WL by 2 is same as 2 multiplied by 6 divided by 2. So we have 2 multiplied by 6 divided by 2. That is, each of the reaction here is equal to 6 kilonewton. So this reaction also equal to 6 kilonewton. Since we are interested at point C here, which one is 2 meter from the left support. So this distance is same as equal to 2 meter. We have left support is at A, and we have UDL here, which has the magnitude equal to W. And we have one reaction is acting vertically upward, that equal to 6 kilonewton. So we'll convert this UDL into equivalent point load. In that case, we'll get a downward force that equal to W. We have W is equal to 2, and we have total length here equal to 2. It means that we have total force acting downward is equal to 4 kilonewton at a distance equal to 1 meter from C. And at point A, we have one vertical reaction that equal to AY, and this value of AY is equal to 6 kilonewton. So exactly at point C, we have to first find out what is the bending moment. So we assume here that we have one vertical reaction, that is the shear force is VC, and we have one anti-clockwise bending moment at point C. Find out this value here, we'll use this FBD. So for this figure, we have sum of moment of all forces above point C must equal to 0. Since we have assumed anti-clockwise positive, so we have a sign convention of anti-clockwise positive. Moment of AY above point C will be clockwise is negative. AY is equal to 6, and we have distance is between A and C is equal to 2. So we have 6 into 2. Equivalent load is 4 kilonewton and will act in a downward direction, so that will produce the anti-clockwise moment, which one is positive value. We have force equal to 4 kilonewton and we have distance equal to 1 meter. And the bending moment at point C we have taken anti-clockwise, so anti-clockwise is positive, so that will be MC equal to 0. In this fashion we can calculate the bending moment at point C. We have minus 12 plus 4. Minus 12 plus 4 is minus 8, that will become positive on the right hand side. So we have bending moment equal to 8 kilonewton meter. Once we know the bending moment and we know the distance y, and this value is come out to be positive, so bending stress at a distance y is given as minus bending moment at point C multiplied by the distance y divided by I. Now this distance is measured above G, so you have to take this value as a positive value. and the bending moment itself is a positive value. So we have minus 8 kilonewton meter is 8 into 10 to the power 6. Y will be equal to 40, and since we have a rectangular cross section whose width is equal to 60, so we have 60, and the depth is equal to 120, so we have 120 cube divided by 12, so 12 will shift in numerator. In this fashion we can calculate this bending stress, and this answer is negative. It means that we have a compressive stress at a distance equal to 40 mm from the centroid or 20 mm from the top fiber. So here you are getting the bending stress at distance y is a negative value and is 37 megapascal. 37 megapascal is a compressive stress. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.